Welcome to CSC 201, Lesson 12.2, Finite State Automata. A finite state automaton is an idealized machine that embodies the essential idea of a sequential circuit. Each piece of input to a finite state automaton leads to a change in the state of the automaton, which in turn affects how subsequent input is processed. So imagine, for example, the act of dialing a telephone. Dialing 1-800 puts the telephone circuit in a state of readiness to receive the final 7 digits of a toll-free call, whereas dialing 413-775 leads to a state of expectation for the 4 digits of a local greenfield call. Vending machines operate similarly. Just knowing that you put a quarter into a vending machine is not enough for you to be able to predict what the behavior of the machine will be. You also have to know the state the machine was in when the quarter was inserted. If 75 cents had already been deposited, you might get a beverage or some candy. But if the quarter was the first coin deposited, you would probably get nothing. A simple vending machine dispenses bottles of juice that cost $1 each. The machine accepts quarters and $half only and does not give change. As soon as the amount deposited equals or exceeds $1, the machine releases a bottle of juice, and the next coin deposited starts the process over again. So the following diagram represents the operation of the vending machine. So each circle represents a state of the machine. So the states of the machine are 0 cents deposited. This is called the initial state, and it's denoted with this little arrow that it's the initial state. And then we have our other states are 25 cents deposited, 50 cents deposited, 75 cents deposited, $1 or more deposited. The double circle indicates an accepting state. So this is what the machine accepts, where something special happens. In this case, you get a bottle of juice. And then the arrows between the different states represent the input. Right? So if you input a quarter, if you're at the 0 cent deposited state and you input a quarter, now you're at the 25 cent deposited state. If from the 25 cent deposited state you input a $half, now you're at 75 cents deposited. And if from here you input either a quarter or a $half, you land at $1 or more deposited and a bottle of juice comes out. Now, at this point, you could input a $half, you could input a quarter, and that would get you back to an earlier state where you would work your way back towards the $1 or more deposited to get another bottle of juice. We can give that same information from the transition diagram using something called a next state table. So here we have our states: 0 deposited, 25 cents deposited, 50 cents, 75 cents, $1 or more deposited. And we notate with the little arrow that this is our initial state, and this little double circle indicates that this is our acceptance state, and then our inputs are quarter and $half. So you would read this as, if you're at the initial state, 0% deposited, and you input a $half, now you're at 50 cents deposited. If you're at 50 cents deposited and you input a quarter, now you're at 75 cents deposited. And if you're at 75 cents deposited and you input a $half, now you're at $1 or more deposited, which is the acceptance state of the machine, and you get your bottle of juice. A general finite state automaton is completely described by giving a set of states, together with an indication about which is the initial state and which are the accepting states, which is when something special happens, and a list of all possible input elements, and specification for a next state function that defines which state is produced by each input state. So this is just a formalization of what we just read up here. Okay, so a finite set I is called the input alphabet of input symbols. Then we have a finite set S of the states. a designated state to be initial, which we call S naught, a designated set of states called accepting states, and then a next state function. So we have a function, n, that goes from S cross I. So my input is a state and an input, and it tells me the next state. So let's use some of these definitions in example. So here I have a finite state automaton A defined by the transition diagram below, and I want to identify the states of A. So the states are given by the circles S naught, S1, and S2. The input symbols are what are on the arrows. My input is what goes on the arrows, so those are just 0 and 1, my input symbols. And the initial state is denoted with this little arrow, so that's S naught. My accepting state is denoted with a double circle, so that's S2. And then this is the function. It's saying find the next state for if you're at state 1 and you get an input of 1. So if we're at state 1 and we get an input of 1, that means you're at state 1, follow the arrow with a 1 on it, and you land at state 2. So here's a similar problem, except this time we're given a next state table instead of a transition diagram. What are the states of A? Those are written vertically, U, V, Y, and Z. What are my inputs? A, B, and C. The initial state is denoted with the little arrow, so that's my U. The accepting states are denoted with the double circle, so that's V and Z. And then I'm supposed to find the next state if my state is U and my input is C. So when the state is U and the input is C, my next state is Y. Okay, so here's another definition. The language accepted by an automaton. If A is a finite state automaton with set of symbols, input symbols I star is the set of all strings over I. And we're going to let W be some string in I star. Then W is accepted by A if and only if A goes to an accepting state when the symbols of W are input into A in sequence from left to right, starting when A is in its initial state. So the language accepted by A is denoted L of A, the set of all strings that are accepted by A. For example, consider the finite state automaton A, defined by the transition diagram below. What state does A go to if the symbols of the following strings are input into A in sequence, starting from the initial state? So I'm going to start my initial states at S naught, and my inputs are going to be 0 and then a 1. So I follow the arrow for the 0, and then I follow the 1, and I land at S2. And then I'm going to do this again. I'm going to start at S naught, my initial state, and I'm going to follow the 0, 0, 1, 1 arrows. So if I start at S naught and I follow the 0 arrow, I land at S1. Then I follow the 0 arrow again, and that keeps me at S1. And then I follow the 1 arrow, which takes me to S2. And then I follow the 1 arrow again, which takes me back to S naught. For number 3, I start at S naught, and I'm going to go 0, 1, 0, 1, 1, 0, 0, which lands me at S1. And then for number 4, I start at S naught, and I go 1, 0, 1, 0, 1, and I land at S2. So which of the strings in part A send A to an accepting state? So the accepting state is S2, so 0, 1, and 1, 0, 1, 0, 1. Those two both landed at an accepting state. So what is the language accepted by A? Well, the definition of the language accepted by an automaton is the set of all strings that are accepted by A. So I have to figure out what kinds of strings land me at S2 when I start at the initial state. So it turns out that any string that ends in 0, 1 will land me at S2 in this case. So the only way to get to S2 is you have to get to S0. You have to get to S1. But once you're at S1, the only way to get to S2 is a 1. So the string definitely has to end in 1. But then from S0, how do I get to S1? The only way to do that is to get a 0. So I could go 0, 1. I could get any number of zeros at S1 and stay here. So I could have 0, 0, 0, 0, 1. So, and I could start at when I start at S0, I could get any number of 1s, 1, 1, 1. When I finally get a 0, I'll go to S1. I can stay there for a while with zeros, but when I get a 1, I go to S2. So anything that ends with 0, 1, it could be a bunch of 1s, then a bunch of zeros, then a 1. So the language accepted by A is the set of all strings of zeros and 1s that ends in 0, 1. Is there a regular expression that defines the same language? So remember the regular expressions was concatenation, star, and the vertical line for or. So I want to express the set of all strings of zeros and 1s that ends in 0, 1. So the set of all strings of zeros and 1s, we can use the notation 0 or 1 star. So you go back to the previous lesson, we derived that this means the set of all strings of zeros and 1s. And I want to concatenate that with 0, 1 because my string has to end with 0, 1. Now suppose a finite state automaton is in one of its states, not necessarily the initial state, and a string of input symbols is fed into it in sequence. To what state will the automaton eventually go? So we have a function that we define as the eventual state function, and you input a state and a string of input symbols, and you output the eventual state. If you start at a given state, follow the symbols, where do you land? So if we consider again the finite state automaton shown below, we want to find the eventual state known as n star, the eventual state if I start at S1 and follow this string of symbols. So I start at S1 and I go 1, 0, 1, 1, 0, I land at S1. Okay, so for this next one, we're going to consider a finite state automaton A shown below, and I want to describe the language accepted by A. So what lands at S0? S0 is the acceptance state. So a language is a set of strings over an alphabet. In this case, my alphabet is zeros and 1s. So what sets of strings land at S0? Okay, assuming we're going to start at our initial state, 0. So we're going to start at the initial state. What kinds of strings land me at the acceptance state, S0? So in order to get back to S naught, I'm starting here. In order to get back, I need to go 1, 1, 1. It doesn't have to be in order because I can have a bunch of zeros at any state, and I'll just stay at that state. But once I get a 1, I move to the next state. So I need exactly 3 1s to get back to S naught. So any number of zeros in between, but exactly 3 1s. Or no 1s, right? If my initial state is S0 and I get a 0, I'm at the acceptance state. Any number of zeros will take me to the acceptance state. And I don't need exactly 3 1s to get back. I could also get 6 1s and go around this circuit twice. Or 9 or 12. Any multiple of 3 1s in the string would get me to the acceptance state. So because the zeros in this particular automaton don't make much of a difference, I can have as many as I want at any point in the string. What really matters is that I have, is that the number of 1s is divisible by 3. So this is going to be the set of all strings, all strings of zeros and 1s such that the number of 1s in the string is a multiple of 3. Okay, which means there could be 0 1s. 0 is a multiple of 3. All right, now I want to write a regular expression that defines this language. So I want to write a regular expression. That was the thing with you can use star, you can use concatenation, and you can use that vertical line for or. A regular expression that defines this. So the first possible way to get to the acceptance state, we're going to start at S naught, a string of zeros of any length. Any length string of zeros will take you to the acceptance state, but that's kind of an anomaly. That's where you never leave the initial state. So you just get a bunch of zeros. As many as you want. You can have a string as long as you want of zeros, and you will land at the acceptance state. So I can define a string of zeros of any finite length as 0 star. If you go back and read the definitions of a regular expression, if you do a string star, that means a finite number of concatenations of that string. Any finite number. All right, so that's one way I could land at the acceptance state, any number of zeros. Okay, and then or I could do any number of zeros, followed by a 1, any number of zeros, followed by a 1, any number of zeros, followed by a 1, any number of zeros. Okay, so starting here, I get any number of zeros. That's 0 star. Followed by a 1, so concatenate with a 1. Followed by any number of zeros, so 0 star. Followed by a 1. I'm going to put little things on my 1s so we don't get confused with the or symbol. Okay, so where am I? 0 star. So any number of zeros followed by a 1, followed by any number of zeros followed by a 1, followed by any number of zeros followed by a 1, followed by any number of zeros. This regular expression would land me at the acceptance state. So we're saying any number of zeros followed by a 1, followed by any number of zeros followed by a 1, followed by any number of zeros followed by a 1, followed by any number of zeros. Now, that only describes exactly 3 ones, not a multiple of 3 ones. So if I want a multiple of 3 ones, that means that I need to concatenate this expression with itself any finite number of times. And the definition of that is star. So I'm just going to put parentheses around this whole string and say concatenate this thing with itself any number of times, and that would land you at the acceptance state. So finally, the big conclusion is Claney's theorem. It says that given any language that is accepted by a finite state automaton, so here we described a language, all strings of zeros and ones such that the number of ones in the string is a multiple of 3. There is a regular expression that defines that language. So here we wrote it down here. And then given any language defined by a regular expression, there is a finite state automaton that accepts that language. So we're not going to do anything with applying this theorem other than this one problem here where we saw that we were able to write down the language for the acceptance language by A, and we were able to translate that to a regular expression, and that's part 1. Okay, any language that is accepted by a finite state automaton, there is a regular expression where you can express that language using it.